Survey of Calculus, Chapter 4, Section 1, Antidifferentiation. The process of reversing differentiation, and remember, differentiation is just taking a derivative, is called antidifferentiation. For example, let's say that f of x is 2x, and capital F of x is x squared would be an antiderivative because when you take the derivative of x squared, you get 2x. So with antidifferentiation, what we're doing is we're saying, this is what I got when I took the derivative. What did I start with? Now, here's the thing though. F of x equals x squared plus 1 and x squared minus 10 would also give you a derivative of 2x, because when you take the derivative, the derivative of a constant is always 0. So since we sometimes don't know or don't have a way of figuring out what that constant might have been, what we do when we do an antiderivative is we say that the antiderivative of 2x is x squared plus c, where c is any constant. And what that does is it accounts for the missing constant that disappeared during the differentiation process. Okay, Theorem 1 says the antiderivative of the lowercase f of x is the set of functions capital F of x plus c, such that when you take the derivative of capital F of x plus c, you get lowercase f of x. Again, the idea behind an antiderivative is you're saying, what I'm starting with is the derivative. I want to work my way backwards to the original equation. The constant c is called the constant of integration. Okay, if two different functions have the same derivative, those two functions must be different from each other only by the constant term. Like we just saw, x squared plus 1 and x squared minus 10 give you the same derivative. So the only difference between the two functions is that constant term. This is a notation thing here. If capital F is an antiderivative of lowercase f, we write that as, and you see here we've got this symbol. It looks like you took an S and stretched it long ways. And you see there the symbolism we use. This is read as the antiderivative of f of x with respect to x is capital F of x plus c. So that elongated S thing is our symbol for antiderivative. It's also, we also use the term integral for it. The left-hand part of the equation is called an indefinite integral. The symbol we use is called the integral sign, and f of x, lowercase f of x, is called the integrand. Okay, so integral is, when you take an antiderivative, you are taking an integral. Those two terms are kind of interchangeable, and we'll probably start using integral eventually more so than antiderivative. This is called an indefinite integral because of that plus c, because we don't know the exact function. We don't know what that constant is. The symbol dx, when you see f of x dx, tells us that x is the variable of integration. Now, we are going to give some rules for integrating, but before we do that, we're going to try a few problems using our knowledge of differentiation, using what we know about how derivatives work. For the problems on the next slide, what you're going to ask yourself is, what would I have to take the derivative of to get this result? Then when you have an answer, you can double check by taking the derivative of what you just wrote down and seeing if you get what you started with. Now, I want you to try to work through these on your own. Don't work to the point of frustration, but try thinking about each one of them. Pause the recording for a minute and then resume, and we'll talk through them. Okay, so for 8, what would you have to take the derivative of to be left with just plain old 8? Well, that would be 8x, because the derivative of 8x is 8. So 8x plus c is going to be our solution for A. For B, okay, think about what happens with powers. When you take a derivative, you bring the power down front and you reduce it by 1. So looking at this, what we have in front is a 3, the power we have is a 2. That must have been an x to the third, because the 3 would have come down front and the power would have gone down by 1. So x to the third plus c. Now, part C should be the easiest of all, because what is the derivative of e to the x? Well, it's e to the x. So e to the x plus c. And then finally D, what gives you a derivative of 1 over x? Well, that would be the natural log of x. So the derivative of the natural log of x is 1 over x, so we have natural log of x plus c. Okay, now here's our rules. First of all, we have the constant rule. The constant rule says that when you take the integral or the antiderivative of a constant, the solution is the constant times x plus c. So in other words, you just tack an x on, because when you take the derivative of a constant times x, the x goes away. The power rule. Now, this power rule works as long as the power on x is not -1. Okay? If the power is -1, we have a different rule. So the integral of x to a power, what you're doing is you're adding 1 to the power and dividing. Now think about it. We're reversing the process. With a derivative, you multiply by the power and you reduce the power by 1. With an antiderivative, you increase the power by 1 and you divide by the power. So it's complete reversal, order and everything. Logarithm rule. Okay, this just says that if you've taken the integral of 1 over x, then it's the natural log of the absolute value of x plus c. For x is greater than, and if you know x is greater than 0, then you don't have to put the absolute value in there. The reason for the absolute value is you cannot take the logarithm of a negative, so you do need to put the absolute value on there. And then the exponential rule for base e. And this actually gives us, well, what if it's not just e to the x? What if it's e to a function of x? Well, it's 1 over a e to the ax plus c. For example, if you had the integral of e to the 2x, it would be 1/2 e to the 2x plus c, because remember what happens is the derivative of e to the x is e to the x, but if the power is anything but just plain old x, you also multiply by the derivative of the power. In this case, we're just looking at a number times the x, so it's just going to get divided. All right, now, having seen the rules, give these a try, and I suggest for part C, you write that as x to the 1/2. Pause the recording, give it a try, and resume to check your answer. Okay, here they are, kind of threw them at you here. X to the 7th, you're going to add 1 to the power, make it x to the 8th, and you're going to divide by 8. So x to the 8th over 8, or 1/8 x to the 8th plus c. Part B, same thing. Add 1 to the power, divide by that new power. And you get 1 over 3.5 times x to the 3.5. Okay, x to the 1/2 plus 1, add 1 to the 1/2 power, divide by the new power. Now this one you kind of get x to the 3/2 over 3/2, which would be 2/3 x to the 3/2. Although your homework program would take the unsimplified version. And for the final one, add 1 to the power, x to the -2, divided by -2. And again, they simplified that, but your homework program should take the non-simplified version. Now try these. Pause the recording, give it a try, and resume to check your answer. Now, they did simplify these a little bit. See, the one I would be concerned about would probably be C and D. C, you may have left it as x to the 7/6 power over 7/6, which would be fine. And D, you may have left that as x to the -3 power over -3, which again would be fine. All right, now try this one. We have an E. Think back to the rule. Pause the recording, give this a try, and resume to check your answer. Okay, so it's e to the 4x, but this time we're going to do times 1/4. And you can always double check these by taking the derivative. If you know how to take the derivative, it kind of gives you a way to make sure you got the antiderivative correct. Now try these. Pause the recording, give them a try, and resume to check your answer. Okay, just double check, make sure everything's okay. So theorem 3, it says a constant factor can be moved to the front of an indefinite integral. So if you have something like c times 1 over x, you can move the c out in front and have c times the integral of 1 over x. Also, if you have two functions added or subtracted, you can take the integral of each individual function. In other words, if you're taking the integral or the antiderivative of x squared plus 3x minus 4, you can split it up and do the integral of x squared plus the integral of 3x minus the integral of 4. And you can split them up that way. You can physically split them up, or you can just think about them, about how you're just going to do the integral of each individual term. All right, knowing that, pause the recording. Now, hang on before you do that. I would strongly suggest for B that you split that up, that you make it 4 over x plus 3x over x plus 2x to the 4th over x. If you will do that, it'll be much easier. Pause the recording, give this a try, and resume to check your answer. Okay, so we're just doing each individual antiderivative. Now, you don't necessarily need to write it broken up like this, as long as you understand that that's what you're doing. The 3 could come out in front, and then you have x to the 6 divided by 6. Then the 7, x to the 3rd divided by 3, plus 8x. And then they simplified it a little bit. 3 times 1/6 is 1/2. 7 times 1/3 gives you 7/3. And don't forget the plus c. It's really easy to forget that plus c, and you do need to include it. So we have 4 over x plus 3x over x plus 2x to the 4th over x. Now the 4 over x, don't make it minus 1 because you can't use a power rule when x is to the -1 power. But what we do recognize is that 4 over x would be 4 times the natural log of x. And then reduce the others. So just kind of follow the process here. So we're taking the integral of 4 over x plus 3 plus 2x to the 3rd, and that gives us 4 natural log of x plus 3x plus 1/2 x to the 4th plus c. Now try these. And we've got a very similar problem for B than one we just did. Pause the recording, give it a try, and resume to check your answer. And here we go. See how you did? If you miss anything, see if you can figure out what happened. So at times we might be given a point that's a solution to the antiderivative. This is called an initial condition. And what that point will allow us to do is to solve for c and get a specific equation. So for example, find the integral of 2x plus 3 dx given that f of 1 equals -2. Now I'll tell you what I want you to do. I want you to go ahead and do the antiderivative and put on the plus c, and then I'll show you where to go from there. So pause the recording, try that much. If you want to try the rest of it, go ahead, but at least do the antiderivative, and then we'll continue. Okay, so the antiderivative is x squared plus 3x plus c. So our equation f of x equals x squared plus 3x plus c. Then what we do is we put in 1 for x and -2 for f of x, because that was the initial condition they gave us. And we just solve for c, and we get -6. Once we know what c is, we go back and write the equation x squared plus 3x minus 6, and that's what f of x is. So that is satisfying an initial condition. That gives us the specific equation that we're looking for. All right, let's try a word problem. In fact, this is a physics problem. You have a rock that is thrown upwards with an initial velocity of 50 feet per second. In other words, when time equals 0, velocity is 50 feet per second, and it's from an initial height of 10 feet. Okay, and that's when time equals 0, height or distance equals 10, and it has a velocity modeled by v of t equals -32t plus 50, where t is the number of seconds after the rock is released, and v is in feet per second. Determine the distance function h as a function of t. Let me remind you that velocity is the derivative of distance. Okay, and then find the height and the velocity after 3 seconds. So find A first. You have an initial condition here, and then find B. Pause the recording, give it a try, and resume to check your answer. Okay, so for A, our formula is we're going to take the integral of -32t plus 50 dt. That gives us negative 16t squared plus 50t plus c. Now, we know that the height is 10 feet when time equals 0. So we're going to put in 10 for h and 0 for t, and we get that c is 10. So our final form of that equation is negative 16t squared plus t plus 10. Then to find the height of the rock after 3 seconds, we just put in 3 for t and solve and get 16. To find the velocity after 3 seconds, well, you just go back to the original velocity equation and put in the 3, and you get negative 46 feet per second. So the rock is 16 feet above the ground after 3 seconds. The velocity is negative, which means it's moving downwards. All right, the rate of change of the population of Arizona is modeled by the exponential function p prime of t equals 0.0416 e to the 0.0315 t. T is the number of years since 1960, so be sure to pay attention to that. And P prime is in millions of people per year. In 2010, Arizona had a population of 6.4 million. Now that is an initial condition. Okay, that is an initial condition. When T is 50 years since 1960, when T is 50, P is going to be 6.4. Find the population model, so take the antiderivative, put in the initial condition, and get a final equation, and then estimate the population in 2018. Pause the recording, give it a try, and resume to check your answer. Taking the antiderivative, the 0.0416 can come out front. Then we know that from our rule for dealing with exponentials, we're going to have e to the 0.0315t, but we're going to divide that by 0.0315. And when we simplify a little bit, we get 1.321 e to the 0.0135t plus c. Putting in the fact that when t is 50, the population is 6.4, we solve for c and we get 0.019. So you see at the bottom our final equation. For part B, we're just going to put 58 in for t and we get 8.19, which means that in 2018, the population should be about 8,190,000 people. This is a summary of what we just talked about. You might want to pause and look over it. If not, continue on and we'll do some additional practice. Okay, pause the recording, go through the problems, check your answer, resume the recording to check your answer, and proceed this way till the end of the recording.